that we have already once again discussed in the previous class. Then we will see regarding types of pre-stressing. So then systems of pre-stressing. What are the materials that should be used for a particular type of concrete? For this type of pre-stressed concrete, can I use our regular concrete, what are the cement concrete, M20 grade, M30 grade, as well as can I use the similar steel HYST bars of FE415, FE500? So similar type of bars can I use or not? We will once again understand that one. Now coming to this stress distribution, the resultant stress analysis in this. Okay, so once again let me repeat what we have discussed in the previous class. Now I am explaining pre-stressing as well as the beam subjected to loading. So when I consider a beam of a cross section A, this is B and D, and A is the cross-sectional area. So now this is the neutral axis. So at neutral axis we know that the strains and stresses are zero. The strains and stresses are zero at the neutral axis. Now here the pre-stressing is done at this point. So when the pre-stressing is done at this point, upon the span length L, and this beam is subjected to a loading W, and this W is nothing but summation of the load, dead load plus live load. And here the pre-stressing is done at the neutral axis with a force of capital P, and L is the span. I am considering it as a simple supported beam. I am considering it as a simple supported beam. So now, when this is a simple supported beam, now if I draw the stress distribution, so when you are drawing the stress distribution, remember, you should first of all draw the cross section. So here the cross section is there. I am just extending the lines here. Now, due to the pre-stressing force P at the neutral axis, there is no eccentricity. So the entire cross section, simple, I am explaining once again. So this is a duster. If I apply a compressive force, so upon a compressive force, the nature of the stress is compressive stress. So the stress is nothing but load by cross-sectional area. Load by cross-sectional area is the stress. So that is P by A. So this is load by cross-sectional area. So the stress is, you can see here, so the force here it is plus P by A. So we call it as normal stress. We call it as normal stress or axial stress. Now along with this one, along with this normal stress, what we are having? We have, that means the bending stress due to loading. Bending stress due to loading. So due to the bending, here there are bending moments due to dead load, bending moment due to live load are happening. The bending stress is nothing but M by I into Y. If this is dead load bending moment, the bending stress due to dead load is MD into Y by I. Mn into Y by I is in case of bending stress due to live loads. So upon understanding of this, so if you draw the stress distribution here, so now in this one, M by I, now if I draw the bending stress, what happens? Now due to the loading, we have already discussed, due to the loading, it will bend like this. So the beam, this is the span L, so due to loading, it tries to bend like this. When it is trying to bend like this, so the top fiber will be under compression, bottom fiber will be under tension. So when the top fiber will be under compression, so the compressive stress distribution will be like this, and here at the neutral axis, the stresses are zero, strains are zero. So this is our distribution diagram, and this is positive, this is negative. And what is the moment here? Summation of the bending moment due to dead load plus live load. So M T plus ml by I into y, md plus ml by I into y. So if you draw the resultant stress diagram, so upon resultant stress diagram, it will look like this. The resultant stress diagram will look like this. So this resultant stress diagram will be, it may be something like, if this value is more negative, then you will get negative value like this. The chance of this diagram, it will be negative if it may be like this also, according to the values, according to the numerical values of L, pre-stressing force P, moments, you may get this is negative, this is positive, and here P by A plus MD plus ML by I into Y. And here also P by A minus MD plus ML by I into Y. What I have written here? I have written this stress distribution at top fiber, at bottom fiber for a pre-stressed concrete beam where the pre-stressing is done at the neutral axis. Under next consideration, this is under case 1 we are doing. Now coming to case 2, when the pre-stressing is done below the neutral axis at an eccentricity of E. So below the neutral axis means instead of here, the pre-stressing is done somewhere here. With an eccentricity of E. So this is, the pre-stressing is not applied at the center, it is applied here like this. So this is your eccentricity E. Now the stress distribution will be not like this. So now for this one, what we are doing, this beam, we can draw an equivalent beam. That means we can change the beam into equivalent beam. How we are doing? Apply equal and opposite forces of P at the neutral axis. Equal and opposite forces at the neutral axis. When equal and opposite forces are acting at the neutral axis, these two forces, they are separated by a perpendicular distance. They will form a couple. So this force and this force, they will form a couple. This force and this force, they will form a couple. And the couple value is P into E. Moment. M is equal to P into E. That's why we have drawn in the previous class the equivalent beam. This is P, this is P. Now these two forces, they are forming a couple, and the moment is here, M is equal to P into E. M is equal to P into E. So how I am drawing the direction? Just see this one. This force is coming like this. This force is going in this direction. So they will form a couple like this. So that is how I have drawn here. They will form a couple like this at the neutral axis. At the neutral axis. Now, for this, if I draw the stress distribution, so this is actually the beam. This is our neutral axis. Now extend the lines. Whenever you are drawing, the cross section of the beam should be there. Why? Because your diagram stress distribution, it doesn't have any meaning when you don't show the cross section of the beam. So you should show the cross section of the beam and draw the parallel lines. Draw the parallel lines. Now understand what is the type of loading here. Don't forget the loading also. Here our beam is subjected to loading. So here what are the forces that are acting under case 2? First one is axial pre-stressing force. The nature of the force is compression. So axial compression pre-stressing force capital P is acting. It will produce normal stress. This normal stress is considered as positive, which is P by A, and we call it as, why I am considering positive? Why? Because in our pre-stressed concrete, compression will be considered as positive, negative will be considered as tension force. So the sign convention positive is for compression, remember here. So now what is the nature of the stress? Normal stress. Plus, along with this normal stress, now what is the second one? See this. Moment is acting. So as eccentricity occurs, eccentricity will produce bending stresses. So due to eccentricity E, bending stress is happening and the bending moment is P into E. So this will be, now you should understand, due to this bending moment, where you will get compression, where you will get tension. So the moment is, just see this one, it is trying to bend the beam like this. Just once again I am showing, it is trying to bend the beam like this. Now you should know where the tension occurs, where the compression occurs. The top fiber will be under tension and bottom fiber will be under compression. So now the top fiber will be under tension. So the sign convention, you should write it as a negative. So this is positive, this is negative. And the value is, we know that this is M by I into Y. So M is P into E. So P into E into Y by I is the bending stress. P into E into Y by I is the bottom fiber bending stress. So I can write down this one as bending stress due to pre-stressing. So that is bending stress due to pre-stressing. Now moving forward, when, okay, this is pre-stressing, that is normal stress due to pre-stressing, bending stress due to pre-stressing. Third one, bending stress due to loading. So when bending stress due to loading is drawn, you will get it as like this. So we know when the loading is happening, due to loading, for example, if I apply a UDL here, what happens? The beam will try to bend like this. So the top fiber will be under compression, bottom fiber will be under tension. So the bending stress is here. This will be MD plus ML into Y by I. This is also MD plus ML into Y by I. So what should I write down for this one? This is bending stress due to loading. You draw this resultant stress diagram for this. Resultant stress diagram is nothing but, now ultimately I am drawing like this. That is assuming that the resultant will be under compression only. Our idea is, if you are doing pre-stressing at any stage, you should not get tension. Remember this one. We should not get tension at any stage. So this should not go beyond tension. Why? Because our concrete is weak in tension, so cracking occurs. So here, why we are developing all these formulae is, based upon these resultant stresses, we will check that under any condition there should be no tension. So if you consider this one, this is P by A minus P into E, plus P into E into Y by I minus M by I into Y. I am writing MD plus ML due to the space restraint. I am writing it as capital M. that is MD plus ML, whereas in the top P by A minus P into E into Y by I plus M by I into Y. So this case 2 condition is very, very important. So what is the here the point is, just understand these two. Okay, let me complete case 3. Once again I will come back to this case 2. So you can write down this one. This is nothing but resultant stresses. You can write down this one as resultant stresses at the top fiber, resultant stress at bottom fiber. Now go to case 3 condition. So keep it as case 3. Pre-stressing force. Pre-stressing force above neutral axis. Pre-stressing force above neutral axis and loading. The cross section of the beam is capital A. This is neutral axis. Now we are doing pre-stressing above the neutral axis with an eccentricity E. Now in this case, P and D are the dimensions of the beam, and L is the span. So this is now we are doing the pre-stressing above the neutral axis at an eccentricity of E. So now you observe this one. This is above the neutral axis. Now the beam is also subjected to loading. This is the condition. Now for this condition, what we need to do? Here I will once again equivalent beam I will write down. This is once again I am taking the simple supported of span L. Now how can we change this beam to equivalent beam? Apply equal and opposite forces at the neutral axis. Here also apply equal and opposite forces at the neutral axis. Now the equivalent beam for this one is so this is pre-stressing force capital P, this is pre-stressing force capital P. These two moments, they are forming a couple, and the moment is nothing but in the same direction of the forces. The direction of the forces are like this. So this is M is equal to P into E, and this is also M is equal to P into E, and the loading is also there. And this loading is WD plus WL. Dead load bending moment plus live load bending moment. Now if I draw the stress distribution for this one, so for this stress distribution, so this is the cross section of the beam, and now for this, due to the application of the pre-stressing force above the neutral axis, first of all here see this one, observe this beam. A pre-stressing force is acting at the neutral axis, so you will get normal stress. So that normal stress is P by A. So we call it as normal stress due to pre-stressing. So that is normal stress due to pre-stressing. That is first one. Second one, we have to write bending stress due to pre-stressing. So bending stress due to pre-stressing, how I will write down here, upon bending stress due to pre-stressing is, now see which fiber will be under tension, which fiber will be under compression. We need to understand what is the direction of the moment due to pre-stressing. Bending, so just understand here, there are two moments that are acting on the beam. They are acting like this. So when they are acting like this, you understand it is coming like this. So what happens is top fiber will be under compression, bottom fiber will be under tension. So when top fiber will be under compression, bottom fiber will be under tension. So what happens here? So you can see top fiber will be under compression, bottom fiber will be under tension, and the value is in the previous case 2, top fiber will be under tension, bottom fiber will be under compression, but this is reverse case. P into E into Y by I. This is P into E into Y by I. Next one is afterwards. This is bending stress due to pre-stressing. Bending stress due to pre-stressing. Now, the next one is we have to write down bending stress due to loading. So it is obviously top fiber will be under compression, bottom fiber will be under tension. This is the same case that we have written. So understand while you are drawing the diagram, don't draw in a rough way. The neutral axis, that means the fibers stresses should be 0. So this will be M by I into Y. Here my meaning is M is nothing but MD plus ML. Dead load bending moment plus live load bending moment. So this is negative, this is positive, M by I into Y. So this will be, now just try to draw this one. What happens here? P by A minus P into E into Y by I minus M by I into Y. So you will get, most probably you will get negative at the bottom fiber, and here this is P by A plus P into E into Y by I plus M by I into Y. Whereas here P by A minus P into E into Y by I minus M by I into Y. So the chances for negative are more in case of pre-stressing, that when it is done above the neutral axis. So here if you understand these 3 conditions, case 1, case 2, case 3, you should have an idea where should I do, that means where should we do pre-stressing, whether along the neutral axis, when above the neutral axis, below the neutral axis. So that means the resultant stresses are to be understood properly. So here under case 3, what is happening? Bottom fiber, the chances for negative is more. So preferably, that means whenever it is required, that is the possible, if you provide the neutral axis, that is if you provide the pre-stressing above the neutral axis, then here negative, the resultant stresses at the bottom fiber are becoming negative. And exactly the value, whether it is of -5, -10, -3, all these things you can only get when numerical values are known. Numerical means a pre-stressing force of 1000 kilonewton is acting, a pre-stressing force of 10 kilonewton is acting. If we know, then only you will understand.